Good morning, everyone. Welcome to the online interactive session on network security and management. Today, we'll have a brief discussion on SHA-512 hash function, message authentication code, and MAC based on block cipher. So SHA stands for Secure Hash Algorithm. It was developed by NIST, that is National Institute of Standard and Technology, and they published this as a standard called as FIPS, that is Federal Information Processing Standard, FIPS of 180 in the year 1993. So there was a drawback of weakness in this. So they went for the revision of the version of this same algorithm and named as FIPS 181, and that they was released on in the year 1995 and referred it as SHA-1. So this SHA-1 has the design structure of it is based on MD4 algorithm, and it also produces a hash value of 16-bit. So even in SHA-1 algorithm, they found a weakness or some drawbacks with that. The another revision version was being released in the year 2002 by NIST and named that standard as FIPS 182, and that they renamed also as SHA-2. So this document is based on the hash function MD4, and it is also same as design function is also closely related to the MD4. So SHA-2 defines three versions of hash value length, which is of 256, 384, and 512 bit, and known as SHA-256, SHA-384, and SHA-512 algorithm. So this SHA-2 algorithm has the same structure, and it has the same type of modular arithmetic operation, and it has the same logical binary operation as we have with SHA-1. There is no lots of difference between SHA-1 and SHA-2. They have all the same criteria of the structure and the arithmetic modular operations of it, but with the higher advancement of the key function and the security part which has been given in SHA-2. Because a research team described an attack in which two separate messages could be found which produces the same SHA-1 hash code. So our main intention over here is, so for a particular plain text, we are supposed to create a hash code which is a unique to that. So when I go back with a reverse order of the hash code, I have to get back my same plain text. But whereas here in SHA-1, a research team has described an attack, so which tells that there were two separate messages for the same hash code, which is a drawback, or it can be a weakness to that. So because of that, they went to shift it to the SHA-2 algorithm. But for our reference, we'll be studying a SHA-512 algorithm. So this algorithm takes an input, a message, with a maximum length or less than or to the power of 128 bits. And it produces the output of 512-bit message digest. So this SHA-512 algorithm processes it in 1024-bit block-wise. So each block, the input value will be 1024-bit. So if it is exceeding 1024 bits, so it will be considered as the second block. So the same process goes on until all your messages gets completed over here. And this process goes on in 80 rounds. So number of rounds we are going to use here is, so 80 ranges means something from 0 to 79. Totally is in 80 round. So each message, a block wise a message is being processed, and I'm going to get back my hash code over there. So in each round, we are going to use three input. So the first input is keyword, that is of DW, which is of 64-bit, and it has been generated from the plain text. This is the first input to the first round. Right? For all the round, it will be the same information. For each and every round, the first input will be the keyword called W, which is generated from the plain text and is of the 64-bit length. And the second input is we are going to use a constant key value K. And the third input is we are going to use a buffer which is used to store intermediate results and output of the hash code. So as we have totally 80 rounds, after each round, it has to store some information. So the storage information, it uses a buffer over here. Once one round get completed, the output of that will be stored in a buffer, and that will be the same input to the next round. So buffer is an intermediate result between the different rounds. For the final round, it stores the output, that is a hash code over there. So these are the three different inputs which has been given to each round, and you will be having 80 rounds. In 80 rounds, you're going to generate you're going to accept the message and you're going to generate a hash code of it. And that hash code you're going to attach to your message, and your message is been transmitted to the destination. So this is a pictorial representation of SHA 512. So here you can see this is your message of L bit. This L bit of information has been appended with 100s, and you have a length, what is a basically message length, which has been appended to your message. So this full information is being divided into number of message blocks. Each messages consist of 1024 bits. So each block, each messages is been given to an input to a function called F function, which also accept initially as initial vector, and from the next round it will be taking the output of the previous round. So once this function accepts these two values, it does 80 rounds over there and produces one hash code. That hash code is being added with your initial vector and it produces one hash code. This hash code is once again given to input to a function called F, and the same process goes on till all your message gets completed over here. We'll see the same methodology in step by step. The first step, appending padding bit. So the message is padded so that its length is suitable to 896 module 1024. So the padding consists of a single 1 bit followed by necessary number of 0 bit. So here you can see once your actual message completes here over here, you're going to add 1 with continuous zeros such that it is the length of 896 module of 1024. The second is append length. A block of 128 bit is appended to the message. It contains the length of the original message, that is before padding. Here you can see this is a length bit which contains the original message length before adding 100, before padding the bits to the message. The length of the message will be updated, will be added at the end of this particular section, which is of 128 bit. The output of first two steps yields a message of 1024 bit in length. So total expanded messages L into 1024 bit. So once I completes with adding concept and adding the length of the original message, the total message should be N into 1024 bits part. The third step is initialize hash buffer. So a 512-bit buffer is initialized to hold intermediate and final result of the hash function. So this buffer can be represented as 8 64-bit register. So these registers are initialized to the following 64-bit integer hexadecimal values as they are shown in the table format over here. So this hash buffer is used mainly to the round function. As I've already told that each and every round function uses 3 input. It also uses a buffer part. which is mainly used to store the intermediate results and the final results. So the intermediate results, all the buffer size will be of 512-bit buffer, and it has been represented with a register values with a register name as A, B, C, D, E, F, G, and H, which is of 8 register. Each 8 register can hold 64-bit of information. Initially, these 64-bit of information is predefined. So that is what is given in this particular table. That is, A holds the value of 6A09, E667F, 3BCC908. The same way, all H value, initial vector value, initialized value will be assigned to all this register. Later on, after each and every round gets completed, the resultant part of that particular round will be stored in this buffer, will be updated or will be overwritten on this particular information. Now, these words are obtained by taking the first 64 bits of the fractional part of the square root of the first 8 number. So now here, these are the 8 registers which holds a 64 bit, and these are the constant. How did we get these values? So these values are got by taking the first 64 bit of the fractional part of the square root of the first 8 prime numbers. That is, I'll be taking the first 8 prime numbers. Once I take the first 8 prime numbers, I'm going to do the square root of it. When I do the square root of the first 8 number, I'm going to get some decimal part of it, some value which contains a whole number as well as the decimal number. I'm going to neglect the whole number. I'm going to take the fractional part of it. So the first 84 bit of the fractional part of the first 8 prime number, the square root of first 8 prime number, is that value which has been stored in this buffer. This is initializing the hash buffer. Initially, these hash buffers are being obtained by this formula. So the second step 4, process a message in 1024. So process message in 1024 bit. So in this step 4, this is the heart of the algorithm, which consists of 80 rounds. So this is labeled as F function. So in this F function, it consists of 3 inputs and it processes 80 rounds of it. And in that input, it also considers as one 512-bit buffer. And these buffer are used to store the intermediate results, and it also stores the final output of it. So at the first round, the buffer has the value of initialized values, the initial value which I've already showed in the table, and each round T make use of 64-bit value WT, which is derived from a message M, and it also make use of the constant K value. So here, apart from the initial vector value, that is a buffer values, it also takes the WT value. So this WT value is of the 64-bit value, which has been derived from the message, which has been taken from the message called M. From a plain text message, I'm going to take the first 64-bit of the information and I'm going to give for the first round. This is the second input. And the third input is the constant K value, which I'm going to give this. Now, when the second input has been told as the message which contains the WT value of first 64-bit will be accepted and it will be given to the first round. Now, which first 64-bit will be considered and it will be given to each round. So that has been taken with this particular representation. That is, this word represents the first 64-bit of the fractional part of the cube root of the first 8 prime number. So the WT value, which is taken from the message, is being taken randomly. So random formulation is, so I'm going to take the first 80 prime number. I'm going to do the cube root of it. So whatever I get the number, the decimal part and the whole number, I'm going to neglect the whole number and take the fractional part, consider the fractional part. So the first 64-bit of the fractional part of the cube root of first 8 50 prime numbers will be the WT value, and which is given to an input to the first round. The same process goes on for all 80 rounds. So the output of the 80th round, that is the last round, is added to the input to the first round to produce the first hash code. That is, the first round hash code is being added by the input to this particular first round information. So when I add these two values, the input and the output, I'm going to get the one set of hash code, and this hash code is being inputted to the next round called F function. The same part has been explained in a pictorial part over here. That is, each round, totally round 0 to round 79, which consists of 80 rounds. In each round, it takes 3 input. One is the buffer value, which consists of 8 buffer values, and it consists of WT value from the message schedule, the message part. It's going to take the first 64 bit of it. This information has been taken by using the formula of the cube root of first 80 prime number and the fractional part of the first 64 bit. So with that part, the information has been taken with the WT and given to the round 0, and you have one more last input as the key value, K value. With these 3 input, it produces the hash code. This hash code will be stored in the initialized in buffer part. So this buffer once again will be an input to the next round. The same process goes on for all 79 rounds. So at the final round, at the 80th round, all the buffer value, which consists of hash code, will be added with the first input part of it. So once it adds all the information, it produces a new hash code. This hash code will be again given to the next process. That is, there is a section. So once this completes with the addition of your output of the hash code and the input of your hash function, so it produces one new hash code, which is an input to your another F function. So this process goes on until all your messages gets completed. So one F function consists of these information. One F function consists of all 79 rounds, and each 79 rounds, it takes the message schedule and takes all 8 buffers and the key values. So the next is message authentication code, that is HMax. Hash function such as SHA1 was not designed for the use as a MAC, so and cannot be directly used for that purpose, as it does not rely on the secret key, so it was not being using over there. So HMax, which stands for hash message authentication code, it is mainly used for the data integrity and authenticity of the data. So the main basic idea of HMax is to reuse the existing message digest algorithm, as well as it also incorporate the key value which has not been used in the MAC part. So it uses the shared symmetric key to encrypt the message digest over here. So HMax is a type of message authentication code which is calculated using a cryptography hash function in combination with the secret key. So it has been named as HMax, that is a message authentication code, as well as with the hash function, the combination of 2 parts, that is creating a hash code with the help of the secret key. Combination of those 2 things gives you a new authentication code function, that is HMax. So the basic design objective of HMax is to use without any modification, to allow for easy replaceability for the embedded part, to preserve the original performance of the hash, and the last, to use and handle key in a simple way. So the HMax algorithm uses some predefined terms which has been listed as H stands for the embedded hash function, that is, we can say it as SHA1 or SHA512 algorithm, and the key is of the secret key value. If the key length is greater than a B bit, so the B bit is nothing but a number of bit in a block. So what may be the size of each and every block for which I'm going to process. So that is a B bit. It should be greater than the B bit. So if it is greater than the B bit, it produces automatically. Otherwise, the padding concept goes on with the key value. And M stands for the message, original message, and the concatenation part, and you have an XOR operation. And I key pad, which is an inner padding, which has a constant value of 36, which is in hexadecimal. And O key pad is an outer padding, which is being represented as 5C in hexadecimal. These two are the constant values, which is being using for a purpose of calculating the XOR operation over here. And there is a new key value called K plus. So this is a key value where the key padded with the 0 on the left side. So as I've told, the key value is being, if it, the secret key value, if the length of it is greater than B, no need of having the padding concept. If it is lesser than B pad, then you're going to add zeros onto the left hand of your particular key value. So that new information, new key will be considered as K plus. So why we have to add zeros onto the left itself? Because as I've given you an example over here, so in hexadecimal, 2 is being represented as 0010. If I add 0 bit to the right, that is 00100, its hexa value will be of 4. The values, the message itself gets changed over here. But if I add 0 to the left of your information, the value doesn't change over here. So the padding concept goes on with adding zeros to the left over here. So that new key value will be considered here as K plus value. So this HMax algorithm works in mathematically as been shown here in the representation part of here. So mathematically it has been represented as HMax, which takes the two input, that is the key value and your message, which produces the hash code. So this hash code is being produced by first taking XOR operation with O key pad, which is a constant value, that is of 5C, which is represented in hexadecimal, and is being XORed with K plus value. This is the first section. The second section is you're going to do the XOR operation with I key pad, which is a constant value, with K plus value. So once you get the values, the resultant hash code of this, the values of doing the operation of XOR over here, the O key pad and I pad, you're going to concatenate the output of O key pad, the I key pad, and your message. This is your message, and these are your hash code. This hash code has been attached to your message, and your message has been transmitted to the destination. At the destination, they're going to take back this particular message, do the reverse part of it, and see whether the same hash code they have found or not. If they found the same hash code, they then come to conclusion that your message is not being altered. If the hash code which has been attached to your message and what they generate at the destination part, those two hash code are of different values, then they come to conclusion that the message is of altered part. The message, someone in the middle part, man in the middle attack, has occurred in this particular section. The same part has been explained in a flow chart. That is, first you're going to do the XOR operation with the K plus value and the iPad value. So before taking the K plus value, we are going to append zeros to the left hand of the key value to create the B bit string to that. So if K is of the length, so we'll take one example over here. If K is of the length 160 bit, now I have to add a padding concept over here because my B bit length is 512 bit. So to satisfy that 512 bit, I have to add some bits of information, zeros bits, to make that my K value is of 512 bit. So here I'm going to add K will be appended with 44 0 bytes. So 44 0 bytes are added to the K to make it as 500 bit. That is, as it is of the byte, we will be multiplying it with 8. That is 44 into 8. We'll be get backing with 352. So 352 bits are added to 160 bit. So we get with 512 bits. So this 512 bits is of the k plus value. So this k plus value, key value, is been XORed with the iPad value, which is of the constant. So this iPad is nothing but all 36 bit, which is in hexadecimal value. So XOR operation goes out with k plus value and iPad value. The output of this will be called as S value. This S is been appended or it has been added to your message. And this message, your message, is been divided into B bits. So according to our example, B is nothing but 512 bits. So my message has been divided into 512 bits. So one block, first block, which consists of 512 bits, second block, which consists of 512 bits. The same process goes on. For this particular message, I'm going to add S value, which is being got by doing XOR operation with the K value and the iPad value. So this full information, that is your plain text as well as your hash value or whatever you call it as a say S value, is been given to a hash function. So I can consider this hash function as such a 512 hash function. So this hash function takes this particular message and initial vector, that is of 8-bit register values, which we have seen previously. All this 8-bit register values with the hash function, which goes with 80 rounds over here. Finally, at the 80th round, it produces one hash code over here. So once I get the hash code over here, the second process goes out over it. That is the K plus part is being XORed with OPAD. OPAD is also a predefined values, which is of 5C in hexadecimal. When I go with XOR operation with these two values, I get the output of some S0 value, which is of the same bit, 512 bit. And this has been appended to my hash code of the previous thing. So these two function message is been given to a hash function of the same SHA-512 algorithm, hash code algorithm, with an initial vector. Same here in this, we have totally 80 rounds with all 8 buffers, and it produces one hash code. And that final hash code is been attached to your message, and it has been transmitted to your destination. Same thing has been explained in a stepwise. So in the step 1, make the length of k equals to b. That has been considered as k plus value, which has been equals to b. XOR the k plus with iPad to produce S1. I'm going to do the XOR operation with k plus and iPad to produce the S1 value. Append message to the S1. I'm be having a message. With this message, I'm going to append, I'm going to add the S bit over here. And then the next fourth step, apply hash algorithm. I can consider any hash algorithm over here. Initially, we have taken SHA-12 algorithm. So with this hash algorithm, it takes all these input as all these message as an input to the SHA-12 algorithm, and produces a hash code. And then the next, in the fifth step, I'm going to do XOR with the k plus value with OPAD to produce the S2 value. Same S2 value is being produced over here by doing the XOR operation with k plus and OPAD. This S2 is being appended to the hash code. That is H, that is your hash code which is got from the step 4, is being added to the S2 value. Last, this full information is been given to a hash function. That is, this full information has been given to a hash function, which produces the final hash code over here. With this, we'll stop this particular topic over here.